So you should see this screen, and I was talking about before I had technical difficulties, how important it is to look at this when we're doing the chain rule about thinking about taking the derivative of the outside function of the inside function times the derivative of the outside function. And let's just read through this, and then we'll talk about it. So a difficulty with Leibniz notation is that it doesn't state specifically where the derivative and the chain rule are supposed to be evaluated. So sometimes it's helpful, or it helps to write the chain rule using the function notation y equals f of g of x. Then dy dx, derivative of y with respect to x, is equal to f prime of g of x times g prime of x. So in words, we differentiate the outer function and evaluate it inside at the inner function, and evaluate it at the inside function, g of x left alone, and then multiply it by the derivative of the inside function. So you'll hear me say the derivative of the outer of the inner times the derivative of the inner when I'm doing this outside inside. Okay, so let's look at some examples. More examples. So what about y is equal to, well, I want to do one with the e. How about e to the square root of x? So my inner function, if I was going to rewrite this as y equals f of x, f of g of x, as a composition of two functions, my inner function, I'm going to write as the square root of x. So g of x is equal to the square root of x. So wherever I see this square root of x, I'm going to write g of x there. Or I'm just going to write x there for my f of x, sorry. So my f of x function is equal to e to the x. So I can say y is equal to f of g of x. Okay, so recall that when we take the derivative of e to the x, it was just e to the x itself. And so if I take the derivative of the outer function, e to the x, this is e to the x. To take the derivative, though, of g of x, we wanted to rewrite that a little bit. So to rewrite it, let's rewrite it with a power instead of a radical. So square root of x is the same thing as x to the 1/2 power. And so using our general power rule, we have 1/2 x, subtract 1 from our exponent. 1/2 minus 2/2 is a negative 1/2. Let's just rewrite this so that it has a positive exponent and a radical instead of a rational exponent. So bringing x to the negative 1/2 power down to the denominator to make that a positive exponent. Using rules of exponent, I have 1 all over 2 x to the 1/2. The 1/2 power is just for the x, so this will be 1 all over 2 square root of x. So if we write this out, dy dx, the derivative of y with respect to x, again, the derivative is f prime of g of x times g prime of x. So this is equal to f prime of our original function of g of x. Our g of x function was square root of x. So square root of x all times the derivative of g of x? Well, the derivative of g of x we found to be this 1 over 2 root x. And we're plugging in square root of x wherever we see an x in our f of x function. So our f of x function is e to the x. And if we plug in square root of x wherever we see an x in here, we're going to get e square root of x all times 1 over 2 square roots of x. I would probably rewrite this as a single fraction. So this is the same thing as e square roots of x all over 2 square roots of x. So let me give you a rule for e. And it will make it easier when we take the derivative. So the derivative of e to the x is e to the x. But if we have the e written as some function f of x, let me see. If we have y equals e raised to some function f of x, when we take the derivative of this, we're going to take the derivative of our exponent, f prime of x, all times our original e function, e to the f of x power. Oops. And so that's a rule. And notice that's exactly what we got. We took the square root of x, the exponent, and we got 1 over 2 square roots of x times the original function, which was e square roots of x, when we did this problem. So let's look at another e one, maybe not as, maybe a little more difficult. I need more room. What if it had been e raised to the sine x? How about, let's even make it even more complicated. How about sine x quantity squared? Okay, so this is, we need to look at the derivative of our exponent times the original e. Let's look at our exponent for a second, because we're actually going to need to apply the chain rule on that piece too. So we have y is equal to sine x quantity squared. So we can use our chain rule there. Chain rule, let's just look at it using the chain rule. So it's outer function, which is this square piece. So the derivative of the outer. So if I bring the 2 down and I subtract 1 from my exponent, this would be just 2 of the inner. I'm going to keep the inside the same, sine x, times the derivative of the inner. So maybe I'm just going to write d dx right here of the inner sine x. And now let's take it. So we have 2 sine of x. And then derivative of sine of x, remember, was cosine of x. So the derivative of e raised to sine squared x is the derivative of our exponent, which we found to be 2 sine x cosine x, times the original function itself, e to the sine squared x, or x quantity squared. They mean the same thing. So this brings us, and I don't know if you notice this, but I kind of use this as the general power in here. And so this brings us that the chain rule, we can use this general power rule with the chain rule. Let me bring that. I know I have it in here somewhere. So the chain rule with a power of a function. So if u is considered to be a differential function that's of x, then we can use the chain rule to extend this power to the power chain rule. So we have some inner function u raised to some power n. We're just going to use the derivative of the outer function, so bringing down our power and subtracting 1, keeping the inside the same, times the derivative of the inner. So this. Okay, so how about y is equal to x squared all over x cubed minus 4x. And then this is all raised to the third power. So first of all, I see that we are going to use a general power rule. And when we take the derivative of the inside, I notice that I have a quotient. So I'm going to have to use the quotient rule. We're going to have to use multiple rules in here to take that derivative. I also notice that we have a factor of x in common in the numerator and denominator. So we technically, from this x cubed minus 4x, we could pull out a single x, giving us x squared minus 4. And so when we have this is x squared over this, right? One of our x's on top is going to cancel with this one on the bottom. So let's rewrite this as a single x in the numerator, all over x squared minus 4 in the denominator, and this quantity cubed. Okay, so derivative of the outer function. So when we look at dy dx, this is equal to the derivative of the outer. So bring down our power 3 of the inner and then subtract 1 from our exponent. So 3 times the quantity x all over x squared minus 4 times the derivative of the inner. So I haven't taken the derivative of the inner yet, but I'm going to take that right now. So we have 3 all times x all over x squared minus 4 quantity squared times. So we need the quotient rule, which is the derivative of the top, derivative of 1 times the bottom, x squared minus 4, minus the top, which is x, times the derivative of the denominator. Derivative of x squared minus 4 is 2x. All over this denominator, x squared minus 4, quantity squared. Okay, so I know we can clean this up. Let's rewrite it that x all over x squared minus 4 quantity squared. We can take the square both the numerator and square both the denominator. So this is the same thing as x squared, right? All over x squared minus 4, that piece quantity squared. Times. So I have x squared minus 4 in parentheses. I guess I don't need the parentheses. So x squared minus 4. And then this minus x times 2x right here, this is minus 2x squared. All over x squared minus 4 quantity squared. So notice my denominator, x squared minus 4 quantity squared times x squared minus 4 quantity squared, same base. Think of that as x squared minus 4. Using rules of exponents, we would add those exponents. So we could really rewrite that denominator as x squared minus 4 raised to the 4th power. And then the numerator, we have this 3x squared here. And let's just simplify inside this parentheses in here, because we have an x squared minus 2x squared. So that's going to give me a negative x squared minus 4. I could technically pull a negative out there. It's not going to help me any to simplify with the denominator. So I would probably leave it like that. So we just found that the derivative of y with respect to x is 3x squared all times negative x squared minus 4, or times that all over x squared minus 4 raised to the 4th. Okay, so this is the chain rule, and this is 3.6 in our textbook. So it really is just doing a lot of problems and these derivatives, because a lot of them now you're going to get into are going to have multiple rules that you're going to be applying. You're going to be applying the chain rule with some quotient rules and product rules and all these different rules. And so it's just a lot of practice, and then hopefully you'll get this down. I will stay after class and I can record more if you want and do more examples.